I would think that if you're using fiber, you probably just use a sort of fiber transmission technology.
Yeah.
I'm not aware of any products that are combining the sort of RJ45 cadex extension technology and the fiber extension technology in one product as a sort of converter. You might get something like a modular matrix where you have some inputs that are HDBaseT and some outputs that are fiber optic. But in terms of transmitting over fiber optics, there are their own sort of chipsets and products that do that.
Yeah, so either or once you have a modular matrix, you can then switch between the two.
Yeah.
Cool. Okay, that's it for me.
Yeah, no worries. Let's move on to fiber optics. So we'll just be going over in some cases with the right SFP modules, you can even go up to 70 kilometers. So what's the physical phenomenon that allows fiber optic signal transmission? It's called refraction. Every material has a parameter called a refractive index, and it's different for each material. And so when you have two different materials like water and air in this example, and you transmit light from one to the other, the light direction, or the direction of the light ray, will change at the materials. And the angle between the directions is determined by the ratio between the refractive indexes. And what we want to happen is what's happening on the right here. So the light ray here hits the surface of the water at a very steep angle below what is called the critical angle. And so it doesn't go out into the air, it stays in the water. So this is called total internal reflection. And this is what we want to happen inside our optic fiber. So we have some real life examples from refraction. I'm sure you've seen some of these before. If you put a pencil in a glass, it looks like the pencil's bent at the surface, but the pencil's not actually bent. It's the light rays coming from the water. Here we've got this guy swimming in his pool. It looks like his head's in a completely different place, but again, this is because of refraction. So when we shine our laser down the fiber, we have light traveling in all different directions. Some travels out of the fiber at the very beginning and is lost, but others stay within the critical angle and reflected all the way along the fiber and out the other end. So we can see now that we've covered refraction, we can compare how this works in the different types of optical fiber. So in the beginning, there was multi-mode step index, which had quite a thick core, relatively, at 200 microns. And it's multi-mode, which means there are multiple paths or modes that the light can travel through the cable. The result of this is there's an increased amount of dispersion. So if we shine some lasers down there, you can see that it's possible for the light to take all of these different paths. So this type of fiber wasn't so great because there was a lot of dispersion. So to improve on it, they came up with multi-mode grade index fiber. And this is where we've got a much thinner core, and there's lower dispersion. And the key difference here is instead of there being a big step between the refractive indexes between the two materials, between the core and the cladding, as you can see on the step index, we've got a sort of a straight line edge where all the refraction and reflection happens. In the grade index, it's happening all the way along the path. So the refractive index of the material actually changes on an atom by atom basis, and so reflection isn't happening at one specific point, but it's happening all the way along the path of the light ray. And then comparing that with single mode fiber, where we've got the very, very thin core, what this means is that light can really only enter at one angle. So there's only one path that the light can take, so one mode, i.e. single mode. And because of this, there's much less dispersion, practically none, and the greatest distance can be achieved. So why does modal dispersion limit the distance that we can achieve? Well, if we take our signal, our input signal, and we send it down the fiber, and the light rays take all these different paths, you're effectively introducing skew into this system, much like with the inter and intra-pair skew from our TMDS, where taking a different path means traveling a different distance and ultimately arriving at the endpoint at a different time. The same thing happens with these different light rays, and when they arrive at the end at slightly different times, that's when they superimpose over each other and cause constructive and deconstructive interference, and that's where the dispersion happens. And the result is, whilst at our input side we had this nice square input signal, at the output we have a sort of wavy sine wave effect going on. However, this particular output signal is still, would still be able to be read. It's not degenerated, but if we had dispersion, you might get a situation like this where it's now not clear what's meant to be a 1 and what's meant to be a 0. So ultimately, this is why signals can't travel as far through multi-mode fiber as they can through single mode. So some of the numbers about optical fiber. The quality of the cable in multi-mode is determined by the OM number. In single mode, it's OS, and generally the higher the number, the better the quality of the cable and the longer the distance you can transmit. So one of the possible problems you might get with optical fiber transmission can be the inaccuracy of the two fiber cables. So if we take a look at multi-mode and we have some misalignment, well, in the perfect world, everything aligned and there's no loss. But because we're talking about the core being in single mode, let's say 10 microns in diameter, all we need is a misalignment of over 10 microns, and now no laser light is getting through.